going to try and get through phase diagrams as quickly as I can while still explaining all the important parts here. So what we have shown on the screen is a generic phase diagram, and what the phase diagram is plotting is where all well, not all, but the three main phases anyway, are present at different temperatures and pressures. So this shows us here that at very high temperatures and really any pressure here, you're going to have a gas. If you heat something up hot enough, you're going to turn it into a gas. But if you have kind of a temperature in the middle and a pressure that's kind of in the middle, you're probably going to have a liquid. Whatever material it is that you are looking at, it'll be liquid. If you heat or if you cool something down very, very low, it's probably going to be a solid, regardless of what pressure it's at. So it's just kind of giving us an idea of where the different phases exist if we were to think about it on a plane of pressure and temperature. So if we're going to look at some real phase diagrams here, CO2, as you can see, looks very similar to the generic one we had back here. All phase diagrams are going to look generally where you have, the solid over here on this side, gas on this side, and liquid kind of wedged between them. They're all going to look similar to that. One unique thing about CO2, though, is that if you notice here, at 1 atmosphere, which is our pressure, the pressure that we exist at, no liquid phase. CO2 actually cannot exist at 1 atmosphere pressure as a liquid. You can force it into the liquid phase and then release the pressure, and it might exist there for a very brief time as it rapidly boils away. But it is never going to exist, especially naturally, at 1 atmosphere pressure. This is why when you take dry ice, which is what solid CO2 is, and you dump it into the water, it just starts to form gas immediately. It doesn't melt. It just goes directly into the gas phase. It sublimes, undergoes sublimation. Water, again, looks very similar, and actually I prefer this phase diagram, even though the units are a bit wonky. It shows a lot more of what's going on. So again, the general shape is the same as any other one. Solids over here on the left at very low temperatures, and especially at high pressures as well. Vapors at high temperatures, and then liquids kind of wedged in between the two. One kind of interesting thing that I do want to point out here is that if you're right at 0 degrees C, where water freezes at the normal point, which is right here, this is normal atmospheric pressure. If you keep compressing the frozen ice that's right there below that freezing point, eventually you can compress it enough where it actually goes back into being a liquid. Again, because water is so unique, because in its solid phase it is less dense than its liquid phase, in some cases anyway. There are actually configurations of ice that are more dense, but common, so to speak, ice is less dense than liquid, and so if you compress it enough, you can actually force it to go back into the liquid phase, which is possible to do, but really not practical. If you wanted to melt it, you better just heating it up a little bit than sticking it in a giant hydraulic press and trying to turn it back into a liquid. You'll end up breaking your press, is all you'll do. Alright, so let's look at a few different points here on a phase diagram, which I don't think... Okay, so this is supposed to be water. Yeah, this is water. So this says, using the phase diagram for water, given this image, it says figure 10.31, that's what this is. Determine the state of water at the following temperatures and pressures. So this is pretty straightforward. It's just saying, at this temperature and pressure, what is its state? So for the first one here, -10 and 50. Well, the markings here are not great, but we can use them. So if this is 0, -10 might be somewhere like here. Oops, go back there. So negative 10 might be right there, and then 50 kilopascals would be somewhere about right there. So that would be a solid at that temperature and pressure. At 25 and 90, 25 would be something like right there maybe, 90 would be about right there, so liquid. And so you can work through the rest of these on your own if you would like. I don't think any of these are really tricky. Let's see, 50 and 40. 50 and 40 might be like right on the edge there, which we'll talk about that in just a second. So that might be something that could throw you off. That's one of the reasons why I don't like this figure very much, is because it's not to scale. So you can see here, this distance is supposed to be 0.01, but then you have 274 here. Like, it's really not to scale. 80 and 5, yeah, that would be definitely a gas. Negative 10 and 0.3, still a gas. I would, well, be right there on the line probably, because again, it's not to scale. So some of these you might say are trying to be right on the line where it's one phase or another, but most of them you can kind of work out how it's just a matter of, you know, it's no different than finding a point on a graph. You just match up the temperature and whatever pressure you have, and where those two meet, that's the phase that exists. Alright, so getting back to the phase diagrams and some of the more interesting regions on these phase diagrams. You might have noticed that on all the ones where it extended that far anyway, you always reached a point where the liquid and gas phase no longer had a solid line separating the two. The reason for this is that for liquids, if you compress them enough and you heat them up hot enough, you will reach a state called what we call a supercritical fluid, where it starts to become more and more gas-like, but it's not really a gas. It's kind of a fluid, kind of a gas, but not really either. It's kind of a mixture of the two. Now these are normally very, very dangerous materials because they have to be very high pressure and very hot, both of which are not very safe. So these are not the safest things to work with, but they can be very useful in certain situations. But supercritical fluids, they're not really their own phase because they don't really have a clear delineation point. There's not really a point where you can say, okay, half a degree ago it was a liquid and now it is supercritical fluid. As you can see here, it's more of like a gradient moving up towards being a supercritical fluid. That line, that differentiation here, so we had gas here, liquid here, and as we heat it up hotter and hotter, they start to become more blurry, where's the liquid, where's the gas. There's not really a clear, now it's the supercritical fluid, and a second ago it wasn't. And so that's why there's not really clear delineation points or lines. You're saying, okay, in this region it's supercritical fluid, but over here it's not. But there is a point where you can say, okay, at this point, right here, at least, this is where that delineation ends, where you can at least very clearly say, okay, now it's back to being liquid and gas. So this, what we call the critical point, is the highest temperature and pressure where you can say for sure that, yes, I do definitely have a gas and I have a liquid. It's not a supercritical fluid. But then once you go past that point, there's not really lines like we have for the rest of the phases to break them apart. Okay, another thing here that I want to point out really quickly is that these lines that we use to separate each of the phases can be used very easily to tell what would happen if, for example, you had a sample, it was at this temperature and pressure, and you heated it up, for example. Well, then it's going to move in this direction, because it would be going to a higher temperature. And so you would go across what we call the fusion curve, which would mean that you melted it. because it's going from a solid into a liquid. And so you can see the same type of thing down here with the sublimation curve, where if you had a sample that was right here at this temperature and pressure, and you started to lower the pressure, but also increase the temperature so that, so that overall it moved in this direction, you would eventually convert that solid into a gas. You would travel over the sublimation curve. And so you can kind of use your knowledge of where the sample starts and which direction it's moving in to figure out what will happen to those materials. Right, we'll call it there for that video, and the next one will very, very briefly talk about solids. I'm not going to get into them in too much depth, but we will discuss those, and that'll be the end for this chapter.